we are going to learn about a new sorting technique called merge sort. Merge sort that is based on divide and conquer policy. What is divide and conquer policy? That we will discuss while discussing this algorithm. So obviously merge sort is a better algorithm than insertion sort because in terms of time it will in terms of time actually, and it is also better than quick sort because I'll tell you how when we'll discuss this quick sort. Then there is an algorithm called heart of merge sort called merging procedure. That is a merging procedure that you have already seen in data structure. Today we will see what is a merge sort and what is the merging procedure. So first I'm going to write this merging procedure. Okay, so let's do that. So what I'll do, I'll write the, how do we write the algorithm? Uh, First, we will write the name of the algorithm. What is the name of the algorithm here? It is merge procedure. I'm not going to write merge sort, mind it. I'm not going to write merge sort. I will be writing a merge procedure. That is a part of merge. Okay? So merge procedure, and I'll pass some arguments to it that are the array, the starting point, and the middle point, and the ending point. Okay, so these are the array that we will pass to get sort. Our problem is to sort the elements. Why we are using another sort? Because this one is better than the insertion sort. This one is the better than, this one is better than insertion sort. In case of we have large number of elements. Okay, in small number of elements, very small number of elements, obviously insertion sort is better. But in this case, the merge sort is better. Okay, so how it is better in terms of time, but it will take more space. I have forgot to tell you one thing, that insertion sort we do not need any other array other than the input size. So that input size, that is called in place algorithms. We are replacing the element in the array itself. We have seen in the insertion sort we were replacing the elements at its own position, this array only. We do not need any auxiliary array, or we do not need any other array other than the array we have taken for input. That type of algorithms are called in place algorithms. And for the algorithms where we need another space other than the input size, those algorithms are called outplace algorithms. Outplace algorithms. So merge sort is an outplace algorithm. This is the difference between insertion sort and merge sort. Also, this is better in terms of time, but it will take more time than the it will take more space than the it will take more time than the more space than the insertion sort. So time is better, but space taken by merge sort will be more than insertion sort. In insertion sort, the space taken was order of big O of n. The worst case will be considered in case of space. There is no best case or no average case in case of space complexity. Okay, so in case of insertion sort, the space complexity was big O of 1, the order of 1, you can say like this. Now I will write this. There is this N1 which is calculated by using midpoint, and there is N2. N2, what are these? We'll discuss it with example. So this is R minus P, R minus Q. What are these? I'll tell you. So this is a starting point, this is a middle point, and this one is a ending point. So ending point minus middle point, there is one length of that, and the first length of from starting point to the middle. Okay, so these are two lengths. So I'll create two arrays, that is left sub array and right sub array of length n plus 1, sorry, n1 plus 1, n1 plus 1, and right sub array, that will be of length 1, 2, and 2 plus 1. Why we have taken n2 and n2 plus 1 and n1 plus 1? I'll tell you with the help of examples. Okay. Now we will take a for loop where we will write I1 to n minus 2, n1, n1, and then I'll copy the elements of my original array, that is A, but I'll divide the whole array because this is a divide and conquer algorithm. So what I'll do, I'll divide this full array into sub arrays, two sub arrays, left sub array and right sub array, and then I'll copy the elements of this full array into left sub array. Half of the elements will get copied into the left side, and half of the elements will get copied into the right side or right sub array. So I'll copy the elements of array from the starting point to the to this I. Okay, I'll discuss that also. Then this is time to copy into the right sub array. Here we will write A of Q plus J. Okay. Then then I'll add the length plus 1 because we have created the array of n1. This is the length of the right sub array, length of the left sub array, and the length of the right sub array. So this one is the left sub array and this one is the right sub array. So uh, half of the elements will get copied plus 1. Why we have taken plus 1? We will copy infinity in the last element of both the left and right sub array. So this is n1 plus 1, and here we will write n2 plus 2, and we will copy infinity here. Okay, we will copy infinity here. After this, we'll write here a for loop starting from k. K is the pointer used to traverse array A, and we'll run it from P to R. P to R is what? Full length from starting point to the ending point. We'll run it from P to R, and then I'll check the condition here. If left of I is less than or equals to R of J, then what I'll do, I'll copy at this array, I'll copy the left of I, and I'll also increment it by 1. Okay. I'll also increment it by 1. Now, if this is not the case, in the same loop, in the same for loop, if this is not the case, then what should happen? Then I'll copy the else. I should copy the right element from the right sub array to this. If the left one is greater, then left will get copied. If right one is greater, right one will get copied, and J will get incremented in this case. So this is our merge procedure. Now I hope I have only written the algorithm. Let me explain it to you how it works. Okay. So I'm going to explain it to you. Now, I hope the screen is clear. Now we have taken infinity here to the left sub arrays last element and right sub arrays last element. Okay, and we have done this. Okay, now we will see the example. So this is our algorithm. Now we will see the example. So let's take an example. So what's happening here? What we are doing, what merge procedure will do, that is called part of merge sort. what it will do, it will only sort two sorted lists. It will only sort two sorted lists, already sorted list. So let's say this one is a sorted list. 1, 5, 7, and 8. So this is the left sub array. Okay. Then the right sub array. So these four elements are sorted. You can see 1, 5, 7, and 8. They are arranged in ascending order. So these are sorted already. Okay. And other elements in the same array are 2, 4, 6, and 9. So you can see these elements are also sorted. So elements from 1 to 4 are already sorted, and elements from 5 to 8 are already sorted. But this whole list is not sorted. This whole list is not sorted. So in order to sort that, what we have done according to this algorithm, we have calculated the length. This one is, let's say, P, and this one is R, starting point and ending point. Okay, according to this array. Now we have calculated the N1 and N2. What is N2? P, Q minus P. Q is the middle point. In this case, that will be 4. Okay, so we want to create actually two sub arrays in which there will be elements. First 4 elements will be there in the left sub array from P to Q, and then from Q plus 1 to R, these elements will be in the right sub array. Let me copy that for you. So this one is L and this one is R, the right sub array. Why sub array? Because it is smaller than this full array A. Okay, this is smaller than this. That's why we are calling it as left sub array and right sub array. So this is left one and this one is right one. What is the length of this right sub array? N1 plus 1. What is N1? P minus Q. What is P here? P is 1. Index is 1. And Q is 4. So 4 minus 1 will be 3. 3 plus 1 will be 4. So just we have calculated the length of length from starting to the middle. You can do it any way. Okay, you can use any way to calculate the length from starting to the middle point. You can do like this from P to R divided by 2. Okay, that will be 1 plus 8 divided by 2. That will be 4.5, and Q will be 4. This is how we calculate 4. Okay, we will calculate 4 in the main merge sort procedure. This is just a merge procedure that is called heart of merge sort. Okay, so this is a merge procedure. What we'll do here? Now we have created the left sub array from 1 to N1, but there is one extra space. At one extra space, we have inserted infinity. So we will insert infinity in one extra space. So there are 1, 2, 3, 4, and 5 spaces. But we have taken this N1 as 4 spaces, and the size of left sub array will be N1 plus 1, and size of right sub array will be N2 plus 1. So at last position we will take infinity. Why we have taken infinity, that I'll also tell. Okay, and practical infinity is not possible, but in case of programming languages we can take any larger value that will be considered as infinity. Or what we can do, we can consider the range of int, because all these elements are of integer type. We can put here the range of int. So whatever is the range of integer that can be inserted here, that will be practical infinity. Okay, so what we'll do here, we'll copy these all elements here. We'll copy all these elements here. How can we do that? We have taken a for loop I equals to 1 to n, 1 to 4. So 1 to 4, and at L of I, L of 1, we will copy the elements from P to P plus I minus 1. That is, if P is 1 and I is 1, that will be 2. 2 minus 1 is 1. So first element will get copied here. then second element will get copied here, then third element will get copied here, then fourth element will get copied here. So we are copying here into the left subarray. So we'll simply copy it. Okay. In a similar way, we have copied the elements from the original array to the right subarray. So these elements will be like 2, 4, 6, and 9. Now we will take a same array A and overwrite it one by one. We will overwrite it one by one. How to overwrite that I'll tell you just now. Okay. So we will copy all the elements here. Now, how do we copy the? This is the same array that I have written earlier, and we are going to overwrite all the elements on this array, and we're going to sort these elements. So what we are doing next? We have used practical infinity at the end of these left sub array and right sub array. This is the next step. After that, we'll go above here. Okay. So we'll go here, and here we will check if left of I is what? First position. If left of I is less than right of I, then what I'll do, left of I element will get copied at P. P is the starting point of array. This one here, it will get copied. So this one is smaller, it will get copied here. This one is smaller, it will get copied. We'll compare this one and this one. This is I and this is J, and this is P and this one is R. Okay, this one is P and this one is R. Okay, is it visible now? Let's see. So we'll copy. I am going to repeat it again. I'll use this K loop from P to R, from P to R, from starting to ending point. Then I will check if the element present at first position of left subarray is smaller than or equals to element present at right first position of right subarray. So whichever is smaller, we will copy it in the A of K. So if left is smaller, we will copy it in the original array and increment I by 1. In this case, we will increment I by 1. So I will be 2 now. So in next point, what will happen? The right sub array, the first element of right sub array is smaller. So this loop will run again, and it will check if L of I is less than R of J. It is not less than. L of I is this. It is not less than R of J. So what will happen? What will happen at A of K? A of K is now what? First it was P. Now it is P plus 1, that is 2. So at second position, we will copy this right subarray's element, that is 2. 2 will get copied here. Now we will increment J by 1. So J will get incremented by 1. J will get incremented by 1. Okay. This position will become J now. Okay, now in the next iteration, what will happen? P will become P plus 2. So this will become P now. Okay, this will become P now. This position. At this position, element will get copied. Which element? Whichever is smaller. So left subarray and right subarray will be compared. So which one is smaller? This right subarray element, that is 4. This one is smaller. So this will get copied here and J will get incremented. Now again comparison will be done. Again comparison will be done. So this one is smaller now. In this case, left subarray element is smaller, and P will get incremented because we are doing the next iteration. So 5 will get copied here and I will get incremented. Okay, and next time what will happen, this will become P now, and 7 and 6 will get compared, so 6 is smaller, 6 will get copied, and this index will get incremented. Okay, and now we have 7 smaller again, and at this position 7 will get copied and I will get incremented. Now I and j both again will be compared. 8 is smaller than 9. 8 will get copied here at the next position and I will get incremented. Now I and j, because only infinity is left, now we need to compare it with the infinity. So 9 is smaller than infinity, 9 will get copied here and I will get incremented, but there is no fun of doing that because our element is already sorted now. So what we have done here, we have used two sorted lists and sort the whole list again. So this is the merge procedure. This is the merge procedure. Now, let me take one more example to show you how this works and why we have taken infinity at the end of these arrays. So I'll take another example in this case. So this is our algorithm. I have already written it, and we will take another example to see the demonstration of why we have taken infinity. So let's take this example. This one is our example here. Let's suppose these are the elements. Okay. These are my elements. So how this algorithm works again? This one is a P, and this one is R, small r, starting point and ending point, and this one is Q, and this one is Q plus 1. Middle and middle plus 1, because left sub array will contain all the elements from P to Q, and right sub array will contain all the elements from Q plus 1 to R. So I'll put these arrays into left and right sub array. So these are 10, 20, 30, and 40, and then infinity. Okay, then 1, 2, 3, 4 in right sub array and infinity. Okay, infinity at the end. Why we have taken infinity? Again, let's see. We'll try to do sorting in this case, and these are 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now we will try to do sorting again. This is I, this is J. What will happen? This element will get compared with this element. Which one is smaller? This one. So this one will get copied here. Okay. Then if this one is getting copied here, I will get incremented. Now position will, we will compare this first element with this element. So 2 will get compared with 10 now. So 2 will be copied here in the next position and I will get incremented. Okay. Then 3 will get copied here and 3 will get incremented because at first position we have 10. I is not incremented till now. Okay. And then this one and this one will get compared. 4 is smaller, 4 will get copied here. Now this list is finished. So if we have not added the infinity, we have nothing left to compare with the left subarray because right subarray is finished already. So that's why we have taken infinity. Now all these elements will get compared with the infinity, which are smaller, and this list is already sorted. So this will get copied here like this, and infinity and infinity will not be compared because the loop is running from P to R, from starting point to ending point. So this many times loop will run. So that's why we have taken infinity at the end of the left subarray and right subarray. So if we do the analysis, there are only two for loops. There is no loop inside a loop. When we'll consider a loop inside a loop, then it will give us a complexity of n square. but here it will take n time of length, n time of length. All other are constant. This will also take n time. Okay, and any this loop will also take n time. Okay, so if we'll press all these and all other will take on, these are assignments. So I've already told you how to calculate time complexity in this algorithm. How do we calculate? We calculate by using how many times number of loop will get executed. Let's say there are n elements here, n elements here, and n elements here. Okay, or we can say there are n by 2 elements here and n by 2 elements here, but here this will run for the n elements. This loop will run for n elements. So if we add all these n by 2 plus n plus n, so this will become something some constant of n. So constants can be noted. So this whole procedure will take order of n times. This only merge procedure will take order of n times. And also we will do the space analysis, space complexity analysis here after we are done with the whole algorithm. This is just a part of algorithm. That is called merge procedure. This is just a part of merge sort. That is called merge procedure. So we have seen the merge procedure. Now we will see the merge sort algorithm itself. So what is a merge sort algorithm? So this one is merge sort, merge sort for what elements? A is an array and there are 3 pointers A, P and R. What is a array? P is the starting point, R is the ending point. Okay. Now what I'll do, I'll check if P is less than R, starting point is still less than R because it will reduce. All the starting points and ending points will reduce. I'll show you how. Okay, with the example. If it is still less than R, if P is less than R, then what should we do? Q equals to floor value of P plus R divided by 2. That is the floor value. If it will be 4.5, then we need to take 4 value. Okay, only 4. If it is 5.3, then also we have to take 5. If it is 5.9, then also we have to take 5. This is floor value. So that this signifies we will be taking floor value. These are not brackets actually. This is the floor value. If I use this one, then this one is a ceiling value. Okay. So after this, we will call merge sort again. We'll do the recursion here. Merge sort again, but for different lists. What are those different lists? The half part, the Q we have calculated. Q is the middle point only. Okay. So we will pass the whole array. Then we will apply merge sort on P. P will be the starting point. What will be the ending point then? Of the left sub array, that will be R. Sorry, that will be Q. That will be Q. So we will call merge sort again, but for different starting and ending point. What will be the starting point? Starting point will remain same, but the ending point is in the middle of the elements. And we will again call a merge sort for the right sub array. We can say that, and it will start from Q plus 1, from middle plus 1 to the last element of array, that will be R. That will be R. So R we have seen that is the ending point. So we have divided the list into 2 parts. This is called divide and conquer. We have divided the list into 2 parts, completely 2 equal parts, middle point and the we have used a merge sort again from starting to middle and from middle plus 1 to R. And then for these two left part and right part, we will call that merge procedure, that heart of merge sort that we have just seen. We will call merge procedure there. Okay, merge procedure. This is merge sort. This is merge sort. We are doing recursion here, but this one is merge procedure that we have already done. So here we will write this one. Okay, so this is merge sort algorithm. This one is merge sort algorithm. How it will solve our problem, we will check it just now. But if we want to calculate its time complexity, how can we calculate its time complexity? If this merge procedure will take total of n time, I have told you how to calculate a recursive function. Recursive algorithms time complexity will make a recursive equation and then solve it. This will take some constant time, so we can ignore this one, and we can also ignore this one. This will take some constant time because this is just a assignment. But we don't know how much time this merge procedure will take, because this list, if this whole list is taking tn time, this smaller list will take tn by 2 time. Then this smaller list also, because this is the right sub array, so this will also take tn by 2 time, and this merge procedure will take order of n. I have just told you in the previous algorithm. This was the previous algorithm that we have called here. We have called that algorithm here. Okay, so this is how we calculate the time complexity. What we'll do, we'll interested in calculating the complete time, that is tn equals to, what is tn now, 2 tn by 2 plus big O of n. Big O of n. This is the equation. By Master's theorem, you can write by Master's theorem. What is Master's theorem? That we'll discuss in the next class. By Master's theorem, it is n log n. Nothing but n log n. I'll also tell you how it become n log n and how to solve this equation. That is also there in the next video. So I'm going to rub this one just then. So this whole time will be tn equals to 2tn plus 2tn by 2 plus order of n, that will become n log n. That is the complexity of merge sort procedure. Now we will see how it works by using an example. You must have noted this down, this algorithm, and based on this algorithm we will solve an example. That is, now we are doing we are applying it on unsorted list actually. So what is a divide and conquer strategy? This divides the problem into two equal parts and then solve these in any number of equal parts, and then solve these sub problems. Sub problems are being solved, and after solving we'll again merge this solution. So this will, the our whole problem will get solved. That's why it's taking lesser time than insertion sort, because in insertion sort it was taking n square. So why we are studying merge sort? Because it is better than insertion sort. Why don't we use merge sort then? Okay, because in smaller number of elements, insertion sort is faster, or merge sort is faster than all other algorithms, even faster than quick sort in some cases. Okay, so this is n square insertion sort and n log n. So if there are n elements, so the complexity in case of insertion sort will be 100, but in this case this will be 10 only, because this is to the base 10. Okay, log of 10, so that is 10. So this one is better, merge sort is better, and it follows divide and conquer strategy. How it is followed, we're just about to see that. Okay, let's say these are our elements. These are our elements 9, 6, 5, 0, 8, 2. 9, 6, 5, 0, 8, 2. These are our elements. What we want to apply merge sort in this. We want to apply merge sort on this example. So how this will happen? Listen to it very carefully. Now, how this will happen? Merge sort will be called. This is our algorithm, merge sort. Okay, for how many elements? For elements from, these are our elements. I've erased it. Let me write it again. Six elements are there. So merge sort will be called for this array A from 1 to 6. You can see from the algorithm. So there was arguments A, P and R. What is P is the starting point and R is the ending point. Yes. So we'll call merge sort for this example. And what will be the P here? P will be 1 and R will be 6. And for every merge sort, three calls will be made. Three calls will be made, function calls actually. We have called three functions. What are those three functions? We have called merge sort again for some list, and merge sort again from for some other list, and we have also called merge procedure for some list. So three function calls are made. So what are those three function calls? You can check from your algorithm. What is the algorithm you have? That is in algorithm, the first merge sort that you are calling is being called from P to Q. So we need to calculate Q here. So what will be Q here? Q will be equals to 1 plus 6 divided by 2. That is 7 divided by 2 is 3 point something. So 3.5 will be there, but we need to take the floor value only, that will be 3. So first merge sort is called from P to Q. So what is Q? P 1, and then what is Q? That is 3. Okay. Now what will be in the second merge sort? It will be Q plus 1. That is 3 plus 1, 4. And to the last element, that is 6. And what will happen in the third function call? That is from 1 to 3 and 6. Merge from 1 to 3 and 3 to 6. So both these lists will be merged here. Okay. How this works again, I'll tell you. Okay. But because this is recursion, function call function itself again. For this function, these three function calls will be there. But these two will not get evoked first. Because this is recursion, so this will go back to this recursion again, because merge sort will call merge sort again, and again for every function there will be three function calls. Okay, so what will be those? Now this will become P and this will become R, and Q will be calculated. What will be Q? 1 plus 3 divided by 2, that will be 2. Okay, so there will be three calls. This recursion will not stop until the exit condition is met. What is the exit condition? That condition is P should be less than R. This is P and R. P is less than R. If P become equals to R, then only this recursion will stop. Okay, then only with this recursion will stop. Now in this case, Q is R, so it will go from 1 to 2, and then 3 to 3, and then from 1 to 2 and 2 to 3. Merge procedure will be called. Again, for every function, three function calls will be there. So what will be happening here? There will be three function calls. Okay. So we can see there Q will become now Q will become 1 now, because 1 plus 2 divided by 2 is 1 point something, that will become 1. No, this will merge sort will be called again, and this will be 1 from list 1 to 1, and from list 2 to 2, and we will merge from 1 to 1 and 1 to 2. Okay, at this point we can see that P and R are equal. Now our condition that we have mentioned in our algorithm, that P should be less than R, is not met here. Okay, so that is the exit condition. So here further recursion will not be there. So function will not call function itself because this condition is met. This is nothing but from 1 to 1. If we can say this, these are the elements 9, 6, 5, 0, 8, 2. If these are the elements. So what is happening? We have divided this into a smaller portion. This whole problem into a smaller problem from 1 to 3. 1 to 3 elements. Okay. Then again we have dividing this problem from 1 to 2. In order to solve this whole problem, we need to solve this sub problem, that is from 1 to 3. But in order to solve this 1 to 3 problem again, we need to solve the problem from 1 to 2. But again 1 to 2, if I want to solve this problem, I must solve from 1 to 1 and 2 to 2. 1 to 1 and 2 to 2. These both have P are equals to R, P is equals to R. So these two functions will not call again itself. So now you can see there is only one element left at the end. We are dividing the list. If there are n elements, we are dividing the list, divide and conquer, into two parts. Okay, then further in 4 parts. Okay, and we'll keep on doing this until we get n by n, that is only one element. So there is only one element. These two elements, only one elements are already sorted. Now we can apply merge procedure here. So the same procedure, and these two elements will get sorted here. Okay. So now we have solved the problem from 1 to 2. Merge procedure we have called from 1 to 1 and 2 to 2. For these two sublists, we have applied the merge procedure, and these two elements are sorted. And then we can see from 1 to 2 list is sorted, and there is only one element from 3 to 3. And we'll apply merge procedure here. What is the merge procedure? This is I, this is j, and there we add infinity at the end. And after adding infinity, we can sort these elements. We can apply merge procedure from 1 to 2 and 2 to 3. So if we apply merge procedure here, what will happen? If we apply merge procedure here, what will happen here? So if we apply merge procedure here, so we will have our sorted list, sorted left subarray here. Okay. Now after sorting this, after we are done with this, we'll go back here and then here. Now we will deal the other half, that is from 4 to 6, 4, 5, 6, these elements we will deal, because this is divide and conquer strategy. What will happen here? We will apply all three function calls here. What are those three function calls? So we will calculate Q here. 4 plus 6 is 10. 10 divided by 2 is 5. So this is from 4 to 5, and this one is from merge sort is for 5, 6 to 6. Q plus 1 to R, and merge procedure will be called for 4 to 5 and 5 to 6. And again this, because P is still less than R, this is true. So again three calls will be there. Three calls will be there. What are those three calls? Again, three function calls will be there. What are those three function calls? Merge from 4 to 4, and then merge sort of 5 to 5, and merge procedure from 4 to 4 to 5, 4 to 4 and 4 to 5. So this is the merge procedure. Here recursion will end because P is now equal to R, P is now equals to R. And in order to solve this problem from 4 to, in order to solve this problem from 1 to 6, we need to solve this one. We have already solved this one. Now we want to solve from 4 to 6. 4 to 6. In order to solve 4 to 6, we have to solve 4 to 5 and 6 to 6. 4 to 5. This is 4, 5 and 6. 4 to 5, and 6 to 6. That is this third element. Now, in order to solve 4 to 5, we will solve 4 to 4 and 4 to 5 first. If 4 to 4 and 4 to 5 are single elements, they are already sorted. Now we can apply merge procedure here. So if we apply merge procedure here, so it will become 0 and 8 here. Those are already in sorted order. And then in order to solve 4 to 5, we have already solved this problem from 4 to 5. This is sorted. Now we will check it with the third element, that is 6, and the merge procedure from this 4 to 5 and 5 to 6 will be called, and elements will be sorted here. At the bottom we can write 0, 6 and 8 by applying merge procedure that we have just did. Now we have solved the problem from 4 to 6, whole this problem, and whole this problem from 1 to 3. Now we can apply the procedure for from 1 to 3 and 3 to 6. So 1 to 3 and 4 to 6 actually. So these merge procedure will be called here, and elements will get sorted. So this is our merge sort. This is our merge sort, and this is how the recursive calls will be made, and this is called recursion tree actually. And recurrence relation is the same, how all the function calls will be made. So let's do its space complexity, because it is not a in place algorithm. This is a out place algorithm that we have discussed. What are in place and out place? The any other space, if we are using any other space other than the input size, because we are dividing, we are using a left sub array and right sub array. So I'll say we have, for left sub array and for right sub array, we have taken an array of size n. Array of size n. Here only we have adjusted all the left sub arrays and right sub arrays. We have overwritten all the values, and then we have copied it to the original array. Okay, we have taken only one global array extra. So extra array is taken. So that is that will take n spaces. Okay, n array. If the array size of array is n, so we have taken n auxiliary spaces, and we'll adjust all the left sub arrays and right sub arrays in this global array. Okay, and we'll overwrite it into the main original array. So that's why we have taken only n spaces. But what about function calls? There will be many function calls, and every function call takes a size in the memory. So but in order to understand that, we will see the order of the function calls. What will be the order of function calls? So this one will get executed first. Okay, so I'll mark it 1. Then this one will get executed. So I'll mark it 2 at second position, and then at third position this one will get executed. Okay, but we are not finished with this 1, 2 and 3, and we'll go to the next function call, that is, because we have to come back at this. Okay, so this one is at fourth position, and this one, now this one is finished, because here it will not be any further recursion. Okay, this one is finished. Then 5, let me write it, 4 and 5. Then this one is 6, and we'll go back here. We have already numbered it at number 3, and this one will be 7 and 8. Now we are finished with this. We have once we have traversed back to it. Now we are finished with it. And after 8, we will go here and then here. And this one is 9 and 10, and then this one 11, 12, 13, okay, and 14, 15, and at last this will be 16 after going from this side. Okay, there will be total 16 function calls, but these function calls depend on the size of input. Actually, we have taken only 6 elements, and there are 16 function calls. But what will happen? How these functions get called? Actually, they get called in a stack, in a memory. Okay. So what will happen? Uh, whatever at We will not use any extra space for all the functions. We will take the height of tree. This is a tree actually, you know. So height of tree, that if we calculate the height of tree, that many spaces will be needed in the stack to store this function calls. I'll tell you how. I'll show you how. Height of tree is equals to stack required actually. The stack required is equals to height of tree. That we already know. Height of tree is log n. Height of any tree is log n. How this is log n, that I'll tell you. Okay. But if we have taken this stack, why height of tree? Because at every level, how many levels are there? There are actually 4 levels. So this one is 1, then 2, then 3, and then 4. Every function call made at particular level will require the same space. I'll show you. So this is how it works. Okay. So this is how I have already told you that for left sub array and right sub array, we will be taking an auxiliary array of size n, a global array. That is a different global array. But how many function calls are there, that we are discussing here. And we will add that value that we have already discussed with this one. Okay. So there are 4 different levels. 1, 2, and 3, 4. So there will be 4 elements. We'll push, because this one is coming first. So we will push it in the stack. The first function call, and then the second function call, and then the third function call, and then the fourth function call. Okay. That many function calls, that many spaces we require. But that also depend upon number of input. How this will work now? After 4 will get executed. Which one will get executed? 5. So will the memory will automatically, we will not do this, the operating system will do this. What will happen here? 4 will get popped out of the array, popped out of the stack, and 5 will be pushed here. Okay. After 5 is pushed, 6 will also pushed here. After 5 will get popped, 6 will also get popped here at the top of the array. At the top of the array, because if we pop this one, because this one is finished, and what will be the top? This will become top. At top position, we will insert the next function call. So 5 will be pushed here, and after 5 is done, we will push 6 here at the same location, because this will become the top. This will become the top of the stack. So we are done with this level. We are done with this level. Now function control will go to this 3. So if 3 is now done, because we have solved the problem from 1 to 2, 3 is now done. So 3 will get popped out from the stack. Okay. And now top of stack will become this position. And now after 3, 7 will work. So we will push 7 here. And after 7, 8 will, because we are done with this also. After completing this one, we will push 8 in this stack. And once we are done with the 8, we'll also pop it and we'll come back to 2. And after we are done with the 2, because we are still after we are done with 2, what we will be doing here, we will push 9 here. And because 9 is there, we are not done with 9 yet. What will happen? We'll push 10 here and 11 here. Okay. Then once we are done with 11, we will push 12 at the same point, and once we are done with 12, we will push 13 at the same position, same memory location, and once we are done with the 13, we'll go back to 10, and at 10, because all the function call at same level does not require any other memory space, so this the height of tree will be the space required. We'll see what is the space required. Okay, so after we are done with 10, we will go to the 14, and after we are done with 14, we will go to the 15, and once we are done with the 15, we'll come back here. Now we are done with 9 also, and we'll go to the 16, and last function call will be made here. So this, what is this size? What is this size? This is this space required, or we will say if the number of levels, it will depend upon number of levels of this tree, the recursion tree we have made. This is the number of levels required is the height of tree. So height of tree is log n. Why it is log n? I'll tell you just after this. It is log n plus 1 actually. If you see the formula of height of tree, that is log n plus 1, and the seal value obviously of the log. So this one can be ignored, and it also depends upon number of elements. So if the number of elements in this case was 6, and in this case is any constant k, so that will not affect it. So log n will be the space complexity, and plus that will be plus there is one more procedure called order of n, because auxiliary space is needed. So which one is bigger? Which one is bigger? Log n is bigger or n is bigger? So n is bigger, so we'll consider that this one is the space complexity of n. So it is not taking much space, it is only taking order of n. In the case of insertion sort, it was big O of 1. In this case, it is big O of n, because n extra spaces are needed. So this will not take much space in the memory. Okay. Now let's discuss the time complexity, if it is clear. So I hope this one is clear now. So let me erase this one, and I'll tell you. Uh, if there are n elements, and we divide into two equal subparts, n by 2 and n by 2, and if we further divide it, n by 4 and n by 4, two equal halves in case of merge sort. Okay, so if we further divide it, it will become n by 8, n by 8, n by 8, n by 8. Okay, and at last it will become n by n, that is equals to 1. Only one element will be left here. One element at last, if we keep on doing this, and then we can apply merge sort. Okay, if you can see, this is also sum of series n into n by 2 into n plus n by 2 plus n by 4 plus n by 8 up to 1. So if this is the case, you can write it directly as log n. You can directly write it as log n, and the work done at each level. So we need to merge these elements. So for merging, we have seen the complexity was n. So for merging these, we need complexity of n. Merging these n, merging these n. So what is the height of tree? I have told you that is log n, or you can also consider it as this is the sum of n by 2, n by 4, n by 8 up to 1 is log n. So log n at each level n is required. So time complexity is log of n, and n of log of n, because at each level we have to merge, we have to apply merge procedure, and the height is log n. Or you can consider it this way, let's say there is only, because there are two children of in this In this case, of every node there are two children, so the log base will be 2 here. And if there is only last element, only one element at last and one element at last, and how many elements will be there? There will be n elements, because only one, the size of array is n, and there is only one element. And in order to copy this one element, both these elements, it will, in order to merge this, it will take this many time. And you can see this is level 1, and level 1 is nothing but log 2. You can see, because there are two children, so log 2 the base 2 is 1, so this is level 1. So there will be how many such levels? Let's say above, if we'll go above, so this will be level 2 of 3. Level 2 is nothing but log 4. Okay, log 4. And how many such levels will be there? If we'll go at here level 3, we have log 8 here. Okay, because 3 is equals to 8, and there are two children, so that's why it's log to the base 2. So log 2 is 1 for one level, log 2 is 2, log 2 is, this one is for level 2. For level 2 we have log 4, for level 3 we have log 8. For n levels there will be log to the base n. Okay, and at each level we have to do order of n work, so time complexity will be n of log of n. This is how we can solve the time complexity. But you can see, no matter how if the elements are sorted or not, if the elements are already sorted or not, the average and best case will be always equal, because if the elements are sorted, then also it will divide it into two equal halves, and further it will keep on dividing till we have only one element, that is 1 and 2. And if they are sorted, then also the time complexity will be n log n. So in this case, best and worst case are same. We can write the merge sort complexity is theta of n log n. The average case will be considered in this case. Okay, so this is the time complexity. This is how we do the analysis of merge sort.